particles 1947 to 1960. For a brief period in 1947, it was possible to believe that the major problems of elementary particle physics were solved. After a lengthy detour in pursuit of the muon, Yukawa's meson, the pi, had finally been apprehended. Dirac's positron had been found, and Pauli's neutrino, although still at large and, as we have seen, still capable of making mischief, was basically under control. The role of the muon was something of a puzzle. Who ordered that? Rabi asked. It seemed quite unnecessary in the overall scheme of things. On the whole, however, it looked in 1947 as though the job of elementary particle physics was essentially done. But this comfortable state did not last long. In December of that year, Rochester and Butler published the cloud chamber photograph shown in figure 1.8. Figure 1.8. The first strange particle. Cosmic rays strike a lead plate, producing a K0, which subsequently decays into a pair of charged pions. Photocourtesy of Professor G. D. Rochester, reprinted by permission from Nature. Copyright 1947, Macmillan Journals Limited. Cosmic ray particles enter from the upper left and strike a lead plate, producing a neutral particle whose presence is revealed when it decays into two charged secondaries, forming the upside-down V in the lower right. Detailed analysis shows that these charged particles are in fact a pi plus and a pi minus. Here then was a new neutral particle with at least twice the mass of the pion. We call it the K0. Kaon. Kaon goes to pion plus antipion. In 1949, Powell published the photograph reproduced in figure 1.9, showing the decay of a charged kaon. K plus goes to pi plus plus pi plus plus pi minus. Figure 1.9. K plus entering from above decays at A. K plus goes to pi plus plus pi plus plus pi minus. The pi minus subsequently causes a nuclear disintegration at B, reprinted by permission from C. F. Powell, P. H. Fowler and D. H. Perkins. The study of elementary particles by the photographic method. New York, Pergamon 1959, first published in 1950. The K0 was first known as the V0 and later as the theta 0. The K plus was originally called the R plus. Their identification as neutral and charged versions of the same basic particle was not completely settled until 1956, but that's another story to which we shall return in chapter 4. The kaons behave in some respects like heavy pions, and so the meson family was extended to include them. In due course, many more mesons were discovered. The eta, the phi, the omega, the rose, and so on. Meanwhile, in 1950, another neutral V particle was found, this time by Anderson's group at Caltech. The photographs were similar to Rochester's figure 1.8, but this time the products were a proton and a pion negative. Evidently, this particle is substantially heavier than the proton. We call it the lambda. Lambda goes to proton plus pion negative. The lambda belongs with the proton and the neutron in the baryon family. To appreciate this, we must go back for a moment to 1938. The question had arisen, why is the proton stable? Why, for example, doesn't it decay into a positron and a photon? Proton goes to positron plus photon. Needless to say, it would be unpleasant for us if this reaction were common. All atoms would disintegrate, and yet it does not violate any law known in 1938. Actually, this particular process does violate conservation of lepton number, but that law was not recognized, remember, until 1953. Stuckelberg proposed to account for the stability of the proton by asserting a law of conservation of baryon number assigned to all baryons, which in 1938 meant the proton and the neutron, a baryon number A equal +1, and to the antibaryons proton bar and neutron bar, A equal -1. Then the total baryon number is conserved in any physical process. Thus, the neutron beta decay, neutron goes to proton plus electron antineutrino, is allowed, A equal 1 before and after, and so also is the reaction in which the antiproton was first observed. Proton plus proton goes to proton plus proton plus proton plus antiproton, A equal 2 on both sides. But the proton, as the lightest baryon, has nowhere to go. Conservation of the baryon number guarantees its absolute stability. Recent grand unified theories allow for a minute violation of baryon number conservation, and in these theories, the proton is not absolutely stable. See the article by S. Winberg in Scientific American, June 1981. The experimental situation is discussed by J. M. Loseco et al., Scientific American, June 1985. If we are to retain the conservation of baryon number in the light of reaction 1.24, the lambda must be assigned to the baryon family. Over the next few years, many more heavy baryons were discovered, the sigmas, the xi's, and the deltas, and so on. By the way, unlike leptons and baryons, there is no conservation of mesons. In pion decay, pion negative goes to muon negative plus muon antineutrino. A meson disappears, and in lambda decay, lambda goes to proton plus pion negative. A meson is created. It is some measure of the surprise with which these new heavy baryons and mesons were greeted that they came to be known collectively as strange particles. In 1952, the first of the modern particle accelerators, the Brookhaven Cosmotron, began operating, and soon it was possible to produce strange particles in the laboratory. Before this, the only source had been cosmic rays, and with this, the rate of proliferation increased. Willis Lamb began his Nobel Prize acceptance speech in 1955 with the words, "When the Nobel Prizes were first awarded in 1901, physicists knew something of just two objects which are now called elementary particles, the electron and the proton. A deluge of other elementary particles appeared after 1930: neutron, neutrino, mu meson, pi meson, heavier mesons, and various hyperons. I have heard it said that the finder of a new elementary particle used to be rewarded by a Nobel Prize, but such a discovery now ought to be punished by a $10,000 fine." Source: Les Prix Nobel 1955, The Nobel Foundation, Stockholm. Not only were the new particles unexpected, there is a more technical sense in which they seemed strange. They are produced copiously on a time scale of about 10 to the power minus 23 seconds, but they decay relatively slowly, typically about 10 to the power minus 10 seconds. This suggested to Pease and others that the mechanism involved in their production is entirely different from that which governs their disintegration. In modern language, the strange particles are produced by the strong force, the same one that holds the nucleus together, but they decay by the weak force, the one that accounts for beta decay and all other neutrino processes. The details of Pease' scheme required that the strange particles be produced in pairs. The experimental evidence for this was far from clear at that time, but in 1953, Gilman and Nishijima found a beautifully simple and, as it developed, stunningly successful way to implement and improve Pease's idea. They assigned to each particle a new property. Gilman called it strangeness, that, like charge, lepton number and baryon number, is conserved in any strong interaction, but unlike those others, is not conserved in a weak interaction. In a pion-proton collision, for example, we might produce two strange particles. Pion plus proton goes to cation positive plus sigma negative, goes to cation 0 plus sigma 0, goes to k0 plus lambda. Here the k's carry strangeness s equal plus 1. The sigmas and the lambda have s equal minus 1, and the ordinary particles pion, proton and neutron have s equal 0. But we never produce just one strange particle. Pion negative plus proton does not goes to pion positive plus sigma negative, does not goes to pion 0 plus lambda, does not goes to cation 0 plus neutron. On the other hand, when these particles decay, strangeness is not conserved. Lambda goes to proton plus pion negative. Sigma positive goes to proton plus pion 0, goes to neutron plus pion positive. For these are weak processes which do not respect conservation of strangeness. There is some arbitrariness in the assignment of strangeness numbers, obviously. We could just as well have given s equal plus 1 to the sigmas and the lambda, and s equal minus 1 to cation positive and cation 0. In fact, in retrospect, it would have been a little nicer that way. In exactly the same sense, Benjamin Franklin's original convention for plus and minus charge was perfectly arbitrary at the time and unfortunate in retrospect, since it made the current carrying particle, the electron, negative. The significant point is that there exists a consistent assignment of strangeness numbers to all the hadrons, baryons and mesons that accounts for the observed strong processes and explain why the others do not occur. The leptons and the photon don't experience strong forces at all, so strangeness does not apply to them. The garden, which seemed so tidy in 1947, had grown into a jungle by 1960, and hadron physics could only be described as chaos. The plethora of strongly interacting particles was divided into two great families, the baryons and the mesons, and the members of each family were distinguished by charge, strangeness, and mass. But beyond that, there was no rhyme or reason to it all. This predicament reminded many physicists of the situation in chemistry a century earlier, in the days before the periodic table, when scores of elements had been identified, but there was no underlying order or system. In 1960, the elementary particles awaited their own periodic table.